day, and then it'll be much shorter the rest of the time through. So we've got a few sections or parts of sections to cover over the next maybe couple hours, maybe. If not, I don't think it'll be that long actually. And a little bit more as we go here, more math type stuff going on. So the first section, I've swapped over my paper. I'm gonna dim this. Is that better for you guys to be able to? That's pretty dim there. All right. I look better in the dark anyway. So, I've swapped to some graph paper. You don't technically have to have graph paper for taking notes here. There'll be grids on the labs and things for you to use and stuff. So if you just kind of sketch the coordinate planes, you're going to be okay. So I've swapped to some graph paper on my screen here so that I can be a little bit more precise on what I'm trying to show you. So section 2.1 is where we're at. We're going to talk about rectangular coordinates. Okay. And with rectangular coordinates, we're dealing with the coordinate plane. So I'm going to draw a coordinate plane, vertical axis, and a horizontal axis. This is the x-axis. The vertical is called the y-axis. And then there are quadrants that we're going to deal with, split into 4 parts, the quadrants. They're numbered starting in the top right with quadrant 1, quadrant 2, 3, and 4. And normally they're going to be referred to with a Roman numeral for that number. That's not as hard rule as it used to be. There you'll see sometimes someone say just quadrant 4, and they'll actually have the number 4, not the Roman numeral. But I'm a little bit of a purist, so I like the Roman numeral style of doing things. But it also separates when I'm talking about an x value or whatever. In quadrant 1, remember that the x values are always positive and the y values are always positive. When we're dealing, what I'm referring to is the ordered pairs or coordinates. X first, y second. Always x first, always y second when you're dealing with ordered pairs. And in the second quadrant, the x's change to negatives, the y's are still positive. In the third quadrant, they're both negative. Not necessarily -1, but just negative in general. And in the fourth quadrant, the x values are positive, the y values are negative. Okay. So if just recognizing those sign changes can help you just tell where an ordered pair would be, what quadrant it would be located in. And then knowing your ordered pairs. So the biggest thing here is, just recognizing where an ordered pair is, plotting it on a coordinate plane, and then telling what the recognizing its location. Okay, so what we're going to do here is, with the first example, is we're going to plot the points on the coordinate plane. So I'm going to draw a grid here, and coordinate plane, we're talking about rectangular coordinates. There's several other types of coordinates, polar coordinates or something that you might use if you end up taking a trig class or something like that. They do some things with polar coordinates, which is a circular grid instead of square rectangular coordinates, which is what we're dealing with. So I'm going to list some ordered pairs and put a letter beside them. That letter just indicates what that, when we plot it, we're going to put that letter beside it so we know it's that point. A is 2, 5, B, -3, -5, C, 0, 3, D, let's do 4, 0, E, -4, +2, and let's do one more, F, at 0, 0. And what we're going to do is plot the points on the coordinate plane, and then we're going to go over here and we're going to write beside the ordered pair what quadrant or location that point is at on the grid. I'm drawing myself a little coordinate plane. If you don't have graph paper, just sketch yourself a coordinate plane, and then draw off the X marks, the ticks. Just try to be consistent. You know, when you draw it, they're about the same distance apart. And the y-axis the same way, and just get a sketch. General idea is what we're after here. We're not after, just incredibly specific things. So when I go to plot the point A, 2, 5, I'm going to go in the X direction first. So the X axis, remember, is the horizontal. The Y is the vertical. So I'm going to go 2 in the X direction. It's a positive 2, so I'm going to go to the right 2, and then I'm going to go up 5. And that's where my point A is going to be, is plotted at that spot. What quadrant is point A in? 1. And I'm just going to write that beside the point there. I'll try to kill 2 birds with 1 stone here. Do one example and cover all of this stuff. Okay. And then point B is at -3, -5. So I'm going to go the X direction first, always left and right first. So it's a -3. So from the middle here, I'm going to go to the left 3 right there, and then I'm going to go -5. So that would be down 5. My point would be right there. That'd be point B. What quadrant is point B in? 3. Okay. And then I'm going to go plot point C. It's at 0, 3. So I'm going to start here in the middle. And it says the X value is 0. So I'm not going to move at all left or right. But then I'm going +3 in the Y direction. So I go up here to 3. And I put a C. Where is that at? It's not in quadrant 1. It's not in quadrant 2. It's in between. So it's just on the y-axis is what you would say. It's on the y. It's where its location is y-axis. It's not in a quadrant because it's on one of the axes. Okay. And then the 0.40, I do that. That'd be right here because I go right 4, and then I don't go up or down at all. And that would be on the x-axis. And I'm going to go to the point E, -4, +2, there. And that would be in quadrant 2. And then the last one is point F. And what's the special name for 0, 0? Anybody remember? Yeah, origin. Perfect. So we've plotted some points. We've stated their location. We've done some good work there. All right. Now, in the rectangular coordinate system, we have a couple of formulas that can help us find lengths of lines or certain spots on lines. So we're going to deal with those next. So the distance formula is our first one. And when we're dealing with the distance formula, we're talking about 2 ordered pairs, x1, y1, and x2, y2. Okay, so that just indicates 2 different ordered pairs. The distance between those can be found using this formula: x2 minus x1 squared plus y2 minus y1 squared. Okay, so we're taking the x values, subtracting them, square it. Subtract the y values, square it. Then add those 2 numbers together, take the square root. That gets you the distance between 2 points. Okay, how long the line is that's between those 2 is really what that distance is. Okay, so let's do an example with a couple of ordered pairs. So let's find the distance between negative 2, 5, and 12, 3. So we're going to take our distance formula. We're going to plug in the stuff that we need to do. So the first parenthesis is subtract the x values. 12 minus negative 2 squared. And then the second parenthesis, subtract the y values. 3 minus 5 squared. The good thing about the distance formula is with those squareds in there, you can't screw it up as long as you put x's together and y's together. That no matter whether you did 12 minus negative 2 or negative 2 minus 12, it's going to get you the same answer once you square it. Because it's the distance between those. It's not necessarily what the value of the numbers are. Okay, so if I subtract those, 12 minus negative 2 ends up being 14 squared. And then 3 minus 5 is negative 2 squared. If I've done it the other direction, I still get 14 and 2, but the signs are different. But when you square it, remember when you square anything, the number always turns positive. So it takes care of it. As long as you get x's together on distance formula and y's together on distance formula, you're okay. And so when you square 14, 14 squared be 196. And I know negative 2 squared is 4. So that ends up being the square root of 200. That'd be the exact answer. We could get a decimal approximation for that. And you know, to do a square root with the graphing calculator, there's not just a single button you have to press. You have to press the second button, which is the blue button, and then the x squared button, and that gets you a square root of 200. And hit enter. And it's about 14.14. So those are, there's the exact answers, the square root of 200, or about 14.14 as the distance between those two ordered pairs. So very straightforward. It's going to be take two ordered pairs, find the distance between them. Not anything, extremely strenuous just yet with distance formula. I think in maybe Math 110, there's a little bit more to do there, but not with us in 100. It's just pretty straightforward. Okay. The other formula that's important when talking about rectangular coordinates is the midpoint formula. The midpoint formula finds the distance halfway, or finds the point that's halfway between two other points. And it's an ordered pair. Where the distance formula is a number answer, the midpoint formula is going to get us an ordered pair formula, a point. It's a midpoint formula, so you're going to find the point that's in between. So what you do is you just take your x values and you add them together, divide by 2. You take your y values, add them together, divide by 2. And that's going to get you the midpoint between any two ordered pairs. Okay. Let's take an example of that. And let's say find the midpoint between 8, negative 4, and negative 6, 1. So very easy to do. Just take the two x values and add them together. 8 plus negative 6 divide by 2. Do the same thing with the y values. Negative 4 plus 1 divided by 2. And simplify. 8 plus negative 6 is 2. 2 divided by 2, 1. Negative 4 plus 1 is negative 3. And divided by 2, it doesn't go evenly, so I'm going to leave it as an improper fraction. We're using the same kind of idea as we did before lunch. about leaving as an improper fraction. So that would be the midpoint between those 2 points. Okay. All right. Let's look at finding a missing endpoint. If we're given the midpoint and one of the other endpoints, can we find the missing endpoint? That's a little bit more difficult thing to do here, but that's where they extend the midpoint formula for us. So keep in mind, you might want to go back and watch this again when you start doing some practice with this part. Find the missing endpoint. So what they're giving us here is an endpoint of negative 612 and a midpoint of 8, negative 2. We've got to find the other endpoint that would work for this. So what we want to do is thinking about the midpoint formula. For the x value, you've got a formula for that. For the y value, you've got a formula for that. So what you can do is set up 2 different problems, one that does the x's and one that does the y's, and you'll find that ordered pair. So to find the x coordinate, we'll start with that one. You're going to set up the midpoint formula for the x coordinate. So the endpoint you have is negative 6 plus x. We don't know this x. It's the missing part. Divided by 2. But we know that the midpoint is equal to what in the x coordinate? What's the x coordinate of the midpoint? It's 8. So we set that thing equal to 8. And we're going to solve this equation. So this is where we're doing a little bit more mathy stuff. Solving that equation. So the first thing that I would do is get rid of that 2 that's in the denominator. They're dividing by 2. The opposite of division is to multiply, right? So if I multiply both sides by 2, it'll cancel that out. Turns this into a 16. And then that's negative 6 plus x. How do I get the x by itself over here on this side? How can I get rid of this minus 6? The opposite of a negative 6 would be a positive 6, right? Yeah, I would add it to both sides. Technically, I'm adding it to both sides, and that gets rid of it over here, and 6 plus 16 would be 22. That's the x value of my other endpoint. I'm going to do a very similar thing for the y value. I'm going to set up the y value of the endpoint I know is 12 plus y, all divided by 2, is equal to the y value of the midpoint, which is negative 2. The work is almost identical. First thing I want to do is get rid of the 2 that's in the bottom. So the opposite of dividing by 2 is multiplying by 2. So that's 12 plus y is equal to negative 4. And then I want to get y by itself. So how do I get rid of the 12? Yeah, subtract 12 from both sides. There's y by itself. Negative 4 minus 12, negative 16. So the missing endpoint x comma y. Remember, x comes first. So that'd be 22, negative 16. And that's the endpoint that they didn't tell us about. Out there. Setting up those equations is going to work the exact same way every time you have to do that. You're not going to have to do that a ton. You're going to be asked more to do the straight up distance formula and the straight up midpoint formula, but that is something that you are going to encounter in this course, is being able to find the missing endpoint based on that. Okay. All right. Well, let's look at graphing an equation. Still the same section, using rectangular coordinates. Let's graph an equation or two. All right, so example E, let's say we had y equals 4x minus 1. And we want to graph that equation. And one of the best ways to graph an equation on the coordinate plane is to use a table of values. I know there are other ways to do it, but I'm going to use this way for now. And then, so I'm going to use a table of values. So I'm going to pick some x values and find the y values that go with it. So I'm going to pick, 3 or 4 x values. I'm going to say -2, -1, 0. Let's just go +1 and +2. There's 5 of them. That shouldn't be too bad. That'll give us a good idea of what this picture is going to look like. So if I've got x values, how can I get the y values that go with them? Well, I could take this -2 and put it in the place of x in the problem, and then I've got a number that's going to work out, right? So it'd be 4 times -2 and then -1, and that would give me a number for y. So that's what I want to do. I want to take those x values and put them in the place of x in the problem. So 4 times -2 minus 1. I've got to follow order of operations. So all that stuff we talked about this morning is back in play. 4 times -2 is -8. -8 minus 1 be -9. Then I'm going to do the same thing with -1. 4 times -1. That'd be -5. I'm going to do 0. That'd be -1. I'm going to do 1. That'd be 3. And I'm going to do 2. That would be 7. So I've got some ordered pairs here that I can plot on the coordinate plane. I've got ordered pairs, -2, -9 is right there. -1, -5. 0, -1. 1, 3. And then 2, 7. Notice how all those dots line up. It should on this one, because that graph is a straight line. Not necessarily always going to be a straight line, but in this case it is. And I just connect all those dots with a line, put arrows on each end because it's going to keep going. And I've graphed that equation for those particular x values, and really any x values if I keep following the red line that I've drawn. It's the same. So getting some x values, plugging them in, and getting the y values to go with them so that you can get the picture of the graph, what it's doing out of there. Let's take a different graph. Maybe it's a little bit more complicated equation, but the idea is exactly the same. What I want you to get out of this is that it doesn't matter what the equation is. If it asks you to graph it and you have no other ideas about how to do it, you can always pick x values and plug them in and get some of the picture drawn. So let's take a different equation. Y equals x squared minus 4. I've been at this a while. I kind of know what that graph looks like. But maybe at one point in life you did know what that graph looks like. Maybe you don't now, and that's okay. Because it doesn't really matter if I know what it looks like or not. I know how I can get the picture of it is by just making a table of values and picking some x's to get y's with. And I'm going to pick the same 5x values that I did before. -2, -1, 0, 1, and 2. And I'm just going to plug those into that problem and work them out. So it'd be -2 squared minus 4. That'd be 4 minus 4 is 0. And then I'd put -1 squared minus 4. Be 1 minus 4 is -3. And then I plug a 0 in. That's -4. I'll plug a 1 in. 1 minus 4 is -3 again. And plug a 2 in. 4 minus 4 is 0 again. You repeat some y values there, and that's okay. It doesn't really matter that it does that. They're in different spots. So I'm going to do -2, 0, 1, -1, -3, 0, -4, +1, -3, and 2, 0. I get this kind of U kind of shape out of it. It's not a V because the lines are, it's not the same kind of slope in between those two. It's more of a U shape out of that. And that's the graph that we get from example F. Just picking X values and plugging them in, working it out. If you're unsure of your graph, plug in some more X values. You can plug in as many X values as you want to get the picture of the graph going on. As we move forward here, you're going to pick up some, okay, I know this graph always looks like this sort of thing, and then you can make some changes as far as that goes. So that gets us through some rectangular coordinates. All right. Now, the next thing we want to look at is a section about functions. So I'm going back to regular paper here, not doing any graphing in this section, not any strenuous graphing. We're going to do some sketches of some graphs, but nothing incredibly precise as far as specific ordered pairs type thing. So 2-3 is dealing with functions. Functions have origins with things that are called relations. And a relation is just a set of ordered pairs. Relations are a set of ordered pairs. Now, when you're dealing with a set of ordered pairs, curly braces, and then each element is going to be an ordered pair. So we would have like 1, 2, comma, and then another ordered pair, 3, 4, and then maybe another ordered pair, 5, 6. That's a good example, of a relation. So it's a set of ordered pairs. Didn't really have any definition to it other than that. It's a set of ordered pairs. That's a relation. Okay. Inside of every relation, there's things called a domain, and there's things called a range. Okay. The domain of the relation is the set of x's, all the x values. So set, so that's curly brace, the x values, 1, 3, 5. That's the domain. Domain deals with x. So range must deal with the set of what? Y's. Yeah. Set of the y's. So just curly brace. The y's are 2, 4, and 6. Okay. So we have domain is the x values. Range are the y values. Okay. All right. Now, every relation is a set of ordered pairs. The title of the lesson or this section is functions. So there must be something special about a relation that could be called a function. Okay, so functions is a relation in which one value from the domain corresponds to one value from the range. The way that I remember, that's kind of a wordy definition. The way that I remember this is functions don't repeat x values. If you want to function properly, don't repeat your x's. That's a good way to think about that. I always tell my high school kids that about dating advice because they're all starting to date about that time. So, if you want to function properly, don't repeat your exits. So not necessarily always true in social situations,
Your
but
meeting has ended.
oh no, we lost our Jackson folks.
I have to call them because I guess they programmed it in for the class, not
The lab.
not the lab.
Okay. Can you not just connect it to it through the Cisco thing?
Yeah, I guess I could, but it's gonna be, I think they changed that. Let me see. Okay, nuisance.
Welcome to a Cisco meeting. You are entering the meeting now.
Programming separately.
Okay.
We'll have to-
Are you back? All right.
We're back.
All right. Good deal.
We'll have to remember that.
Yeah, we will. All right. All right. All right. Now, so I didn't do anything while you were gone. So don't repeat your x values. If you're going to be a function, you can't have repeated x values. It's okay to repeat y values, but not x values to be a function. So what we're going to do is we're going to look at a few functions or a few relations and decide, are they functions? So I'm going to answer this question. Is this a function? And then, of course, the teacher question, why or why not? So always it's a good question to ask. So we have ordered pairs 1, -6, 3, 5, -2, 4, and 7, -13. So here's our relation that we have here, and we want to decide, is this a function or not? So we're looking at what values to decide if this is a function. The only one that matters is the x values. So are there any repeats? There's a 1, 3, -2, and 7. Are those all different? Yes. So yes, it is a function. No repeated x values. And what's no repeated x's? That's why it is a function. No repeated x's. Very easy to tell that. Sometimes a relation might be given to you in a table form, like we used in the last section when we're graphing lines. In my opinion, easier to read than the set of ordered pairs written out with parentheses and commas and all that stuff in it. Is this a function? Yeah. Same reason. No repeated x's. Easy stuff so far. Example C, they might give you an ordered pair or a relation in what's called a mapping. Okay, and with the mapping, they have a domain and a range bubble. A bubble for each of those. So the domain bubble and a range bubble. And the domain just has the x values that are in the relation listed. The range bubble has the range values that are listed. And then the mapping is arrows drawn to the corresponding parts for those. So maybe they've got an arrow drawn from 3 to 7, and then from -8 to -5, 10 to 2, and 6 to 7. Is that a function? Why not? If you say it's not. Am I using the -6 twice? I'm using the 7 twice. Which 7 is a what kind of value? A y value. Is it okay to repeat y's? Yeah, it is. It's legal to repeat y's. You can't repeat your x's. Okay. So no repeating x's, but it's okay to repeat y. So this is yes, it is a function. No repeated x's. Okay. Yeah, and that's the key is you got to watch out for because they're going to repeat x's sometimes and repeat y's. If I just add one more arrow to this, and say, okay, well, I'm going to take the 10 to the 7 as well. Is that a function?
No.
No. What x value repeats? X value of 10 repeats. So that means it's not a function. So that's what you're looking for here in a relation is saying, okay, well, are there any x's repeated? If there are, it's not a function. If they're not, if like example C, you got y values repeated, that's not a problem. Y values are okay. X values are not. Okay. So we've seen relations listed as a set of ordered pairs, as a table, and then here we've had a couple examples of the mapping. Another way that a relation could be represented is a graph, and I'm just going to sketch a graph here. It doesn't have to be perfect. You just get something that looks similar to what I'm drawing here. So I've got a coordinate plane here, and I'm not even going to put tick marks on it or anything for that reason. Just I've got a coordinate plane, and then I've got a line drawn on it, a diagonal line of some sort. Just make yours look something like that. Now, that blue line that I've got drawn there is a relation. It represents a whole bunch of ordered pairs. Okay? You wouldn't be able to list all of the ordered pairs that it represents. So there's got to be a better way to determine if that is a function or not. And there is. There's this thing called the vertical line test. The vertical line test, what you do is you take a vertical line and you drop it everywhere on that graph. So I would just take a vertical line and just try to find a spot where if I drop a perfectly vertical line, how many places is each individual vertical line touching that blue line? Well, this one only touches it once. This one's once. What that determines is that if the vertical line only touches it one spot, then it passes and it is a function. Okay? And that means it has no repeated x values. Let's look at a graph where maybe there is a problem. And I'll show you what fails the vertical line test. So you got a coordinate plane. And again, I'm just kind of rough sketching something here. And then you've got this kind of graph drawn. The blue part is the relation. If I put a vertical line right there, how many places does that red vertical line touch that blue graph? 1, 2 times. What that means is that x value is used twice. It's got 2 different y values for that same x value. So that fails the vertical line test. So this is not a function. So if you're trying to test to see if something is a function or not, and you've got a graph, the vertical line test is the best way to test it. Just go for the vertical line and see, if it touches it twice, it fails. It's not a function. If you can put it anywhere on the graph and it touches it twice, because there is one spot that you can put a vertical line and this only touched once. If I put the vertical line right there, it only touches that blue part one time. But there is somewhere that I can put that vertical line and it touched twice, and that's what makes it fail. Okay. On the previous example E, I couldn't put the blue line anywhere that touched twice, or the red line to touch the blue line anywhere twice. It could only touch it once anywhere I put it. Not anything just incredibly strenuous about that. Let's look at a couple of graphs and talk about some domain and range that's involved with a particular function. with that, just based on that sort of stuff. So example G, I'm just going to sketch a graph, and I'm going to point out the spot that's important here. I've got a U-shaped graph, and this point right here is -1, -4. That's it. That's going to be important when we talk about domain and range for this one. The first question I have is that a function? Yes, that is correct. It passes the vertical line test. Anywhere I put a vertical line, it passes. Okay, so that passes the vertical line test. So it is a function. Now let's talk about the domain. Domain, remember, is x direction. X is domain. So we're going left and right. This point down here at the bottom, what I'm trying to indicate is that's where it starts changing directions. That's where it's going from going down to turning around and going up. That's what that point's indicating. Okay, so this arrow is kind of pointing up a whole lot, but it's also moving out to the left a whole lot too, right? It's going to keep going further and further out as I go on up the graph. Same way with this one. As I go further, that one's going to drift off to the right a little bit more each time. It's still going to go up, but it's going to go out to the right. Since we're talking about domain, we're only concerned about it going left and right with domain. So the domain of this one is going to be all real numbers because it keeps going forever to the left and it keeps going forever to the right because of those arrows on the end of it. Okay, so our domain for this would be all x's and then a straight up and down bar. That just means, okay, it's x because it's domain, and here's what kind of domain it is. We'll say all real numbers. Now the range deals with what values? The y. So our range, we're going to be writing it like this. Curly braces, y, and then that straight up and down bars technically read such that, but it just means, okay, everything after this is how y works. Look at the lowest y value on the graph. What's the lowest y value? -4. So that's at the bottom of the graph. The graph goes up from there, and it keeps going up in both directions, you know. So we're going from -4 up to technically what would be called positive infinity because you're going to keep going up forever. So our y values are always going to be greater than or equal to -4. So that's how we would indicate that range. We hadn't done that on any of the previous problems just because I was, we're worried more about what is if is a function or not on those. I want to start bridging that into domain and range. So we're going to talk about that next. Okay. So range up and down when you're looking at the graph. Domain left and right when you're looking at the graph. Okay. We're going to look at graphs. We're going to look at some equations in a minute and decide how to find domain and range for those. Mainly domain is our biggest asset for this. Let's look at another graph. A coordinate plane here, just sketching it. All right, so I'm going to plot some points here. That's at 0, 4. That's at 0, -4. That's at 2, 0, -2, 0. And what I'm drawing here is supposed to be what's called an ellipse. Okay, so that's our graph. Is that a function? No, it's not. Fails the vertical line test. There's a good example where it fails the vertical line test. But we could still talk about the domain of that. Now, domain, remember, is left and right. When I look at this graph, the furthest to the left it goes is that point right there, which is -2, 0. So the domain starts at -2. But the furthest to the right it goes is that point right there, which is +2. All the x values are between that. So I'm going to use the less than or equal to signs to get that. That tells me that x is between -2 and +2 based on that graph. Domain and ranges is easier when we start talking about equations. With the graphs, it's sometimes hard to grasp. The domain is easier with the equations. The range, what's the lowest y value? -4. What's the highest y value? 4. So that means it's going to go from -4 up to +4. Y's are in the middle, and just do less than or equal to's on that. If the range is in between two numbers, use less than or equal to marks, or the domain, if the x is in between the two numbers, use less than or equal to marks out of that, and you get the domain and range of those. Okay. Just a second here. All right. Now, let's talk about it with equations. We've looked at a couple with the graphs. It's kind of just, you got to see it and remember, domains left to right, ranges up and down, sort of thing. So with the graphs, you're looking for it. With equations, so domain of equations. When we're looking at equations, there's a couple of red flags that we have to look for, okay? So those red flags that I'm going to look for there's only 2 of them that cause problems with domain. The first one is x in the denominator. And remember, the denominator is the bottom part of a fraction. Only if there's an x in the denominator is there a problem. The other red flag is x's on the inside of a square root. All right. All right. If the green flag I've got drawn there, it says if there are no red flags, then the domain will be all real numbers. And underneath that, I've written -infinity, +infinity. And that's going to kind of bridge us into using interval notation a little bit. We'll talk about that as we go here. Interval notation is just a different way of writing it, but we got to start bridging our way toward that. So the red flags we're looking for are x is in the bottom of a fraction, or x is on the inside of a square root. If the problem doesn't even have fractions in it, there's no red flags. If the problem doesn't have a square root in it, there's no red flags. So the domain would automatically be all real numbers. Okay. So the only times that there's an issue with the domain is when those two red flags occur. X in the bottom part of a fraction. You can have X in the top part, and it's not a problem. It's X in the bottom part that's the problem. Or if there's an X inside of a square root. That's the only time the domain gets messed up a little bit. And we're going to see how to handle that. The rest of the time, the domain is all real numbers. And we're going to write that as negative infinity to positive infinity. We're going to do kind of both sections here, both ways of writing it. Okay, so let's find the domain from the equations is what we're going to be doing here. So keep in mind those two red flags that we have to be looking for. That's what we got to keep in mind anytime we're talking about domain. So find the domain. Okay, so what letter are we on? I. Y equals X plus 4. Okay. Are there any red flags in that problem? No, there's no fraction, so there can't be an X in the denominator. There's no square root, so there can't be an X inside of a square root. So there are no red flags. So that means my domain is X, all real numbers. The interval notation, interval, interval, for that is negative infinity, comma, positive infinity with parentheses on the end. Okay. This is what's called set notation. Remember, because it's got the curly braces on it, set notation. Interval notation is another way of writing that. We got to kind of start inching our way toward writing more stuff in interval notation, because the further we go in the course, the more stuff we're going to put in the interval notation, not just set notation. So we're going to be able to do both of those as we go through this. Okay. So no red flags on that one. So the domain was all real numbers or negative infinity to positive infinity. Let's look at this one. Are there any red flags with this one? Yeah, there's a red flag right there on the bottom. Got an X in the denominator. That's a problem. Okay. The problem occurs in what's the only number that we can never divide by? Anybody remember? The bottom of a fraction can never be 0. We can't, dividing by 0 is not a defined operation in math. So that denominator having the X in it, depending on what X is, it could turn into 0. The bottom part of that fraction could. What we've got to find is what number makes the denominator 0. In order to do that, all you've got to do is set the denominator x plus 2 equal to 0 and solve that problem. Not very strenuous, pretty easy to do. Subtract 2, x. If x is negative 2, the denominator equals 0. So what that tells me is in the domain, in set notation, x can be anything as long as it's not negative 2. And that just says x such that x does not equal negative 2. As long as x is not negative 2, we're okay. Now, in interval notation, that's a little tougher to write. And so the way that works is what you've got is you got the original domain of every function is negative infinity to positive infinity. So you've got this number line going along here, and down here is negative infinity up here is positive infinity. There's a -2 in the middle here that we've got to jump over. So when you look at your domain, you've got all of these numbers here, and then you're skipping that one and going on to positive infinity. So that means from negative infinity, we're skipping -2. So we got to get to -2, and then we're going to skip it. So I put a comma, -2, parenthesis, and then here's where I'm using some of my set notation stuff from this morning. Okay. Union, parentheses, -2 to positive infinity. Okay. Whatever number you're going to skip, you got to write it twice in interval notation. Set notation, much easier when you're just skipping a number. When you've got a little bit more going on, there's some other things going on. The interval notation is easier than the set notation. It kind of bounces back and forth, equals out to where they're both about the same. But whatever number you're skipping is going, negative infinity up to that number, that number to positive infinity. That's kind of the MO there for that. That's what's going to happen when you have an X in the denominator. So how you're going to do it. We're going to look at a couple more examples of this and stuff. So it's not anything incredibly distant when you get time to practice this. Okay, so let's look at example K. Example K. Y is equal to the square root of X minus 5. Do we have any red flags? Yeah, we got a square root right there with an X inside of it. That's a problem. Okay. Anytime it's a square root with an X inside, what you've got to find out is what keeps the inside of that square root positive or 0 or bigger, I guess, but greater than or equal to 0. So you take the inside of that, we set X minus 5 greater than or equal to 0. Okay. Whatever's inside of the square root, set it greater than or equal to 0 and solve it. Get X by itself. X has got to be greater than or equal to 5. Okay. So our domain then, in set notation, X has got to be greater than or equal to 5. Straight, exactly the same thing as you got your inequality. Just copy it over there. In interval notation, X is greater than or equal to 5. So you're going to go from 5 and up. So that's 5 to positive infinity. But there's an equal to mark. So here's where you got to count the 5 is part of the game. So you put a square bracket. That's where the square bracket has meaning. Okay. Square bracket 5, comma, infinity. That means from 5 to infinity, including positive 5. Okay. Parentheses are used when you're not including the number. Brackets are used when you are including the number. So if you use an equal to mark in your inequality, then you have to use a bracket in your interval notation. Okay. So there we've had an example of each of those situations. Let's look at the next thing with only thing that changes on the next example is we write it like this. F of X is equal to 6 over 2X plus 7. What did F of X take the place of? What was over here in the other problems? Y. That's the same thing as Y. It's just function notation for that. It's just writing it in a different notation. It's function notation because we're talking about functions in this chapter or this section. So F of X and Y are the same thing. Are there any red flags in this function? There's an x in the denominator. Right there, 2x plus 7. So I got to take care of that. What do I do with the denominator to take care of that? Good. 2x plus 7 equals 0. And I want to solve that. Subtract 7. Divide by 2 is the last step. So x can't be negative 7 over 2. So our domain will be x such that x does not equal negative 7 over 2. What's the interval notation for that? And I'll kind of help build it here for you. From negative infinity up to the number we're leaving out, negative 7 over 2, union the number we're leaving out up to positive infinity. That's what it's going to be every time with this, that x in the denominator. Let's take another function. Calling this one g of x, just changing the name of it. Remember, that's just the same thing as y. It's not really anything exciting. Plus 3x plus 5 inside of the square root with a plus 8 outside. We want to find the domain of that function. Are there any red flags? There are. Yeah, the 3x plus 5. This square root's the problem. The plus 8 on the outside really doesn't matter. It doesn't affect the square root part. Only the part in the square root. So how do I work out the domain for that? I have 3x plus 5, and what do I do with it? Good job. Set it greater than or equal to 0. Perfect. And then, so I'm going to get rid of that 5. I'm going to have to subtract it because it's plus. And I'm going to divide by 3. So my domain then the set notation is the easy part. You just copy it straight over. The interval notation, it's actually a little easier on this one. Take the number I'm starting with and going up to positive infinity because it's greater than. If it ended up being x is less than or equal to, I would start with negative infinity and go up to that point. It'd have to be a negative in front of the x for that to happen, though. So there's the domain of that particular one. Okay. Let's look at evaluating functions. F of x is equal to 3x minus 7. And we want to find f of negative 2. All right, this is really, really easy. It's back to order of operations things. Again, this is an easy portion of this section. All that means to find f of -2 is put a 2 in the place of x, or a -2 in the place of x, and work it out. So that'd be -6 minus 7. So that'd just be -13, and that's it. That's function value, or evaluating functions, same thing. If you had another function, x squared minus 3x plus 7, and they said find g of 1, where do you put the 1? In the place of every x is where you put it. And just work it out. 1 minus 3 plus 7. Be 5. So evaluating functions, function values, also what that's called. Very, very easy thing. Replace the x with the number that's in the parentheses. You're not trying to get g by itself or f by itself. Don't overthink it. Just plug it in, work out that side, and you've got your function value. Okay. It gets a little bit more confusing, but it's still easy once you've seen it. If you have a function that's listed as a set of ordered pairs, and they hardly ever do this, but they do it once every now and then, and you've got this function as a set of ordered pairs, and they say find f of 3. You don't have a place to plug the 3 into. You don't have an x to just plug it in and work it out. So it seems like it's a daunting task. Remember that that's an x value. So what you do is you go into your function up here, your set of ordered pairs. Okay, where's the x value of a -3? Or I mean a +3. The first one's -3, so that's not it. The second one's 0, that's not it. Hey, there's an x value of a 3. What's the y value that goes with that one? 1. So f of 3 is equal to 1. And you're done. So it's a little bit, it's not straightforward, plug it in, work it out, easy order of operations stuff. But it's even easier because there's no working out to go. You just got to find the right ordered pair. Find the one that has that x value. And if it's a function, it can't have two of them that have the same x value, right? Because remember, x's can't be repeated if you're a function. So that eliminates the confusion on that part. Okay. If they same function, if we've asked for f of 6, what would be f of 6 out of that same function? Find 6. It'd be -1. That's right. Good job. Okay. All right. One last thing in this section about functions, and then it gets a little lighter for the rest of the stuff we're doing today. Is a little bit lighter lifting than what we've been doing here. So, and that's looking at a particular graph and the example Q. And I'm going to draw a little coordinate plane, and then I'm going to sketch a graph over the top of that we're going to talk about. All right. So here we have a graph that would technically be a function, but we're not as concerned about that. What we're looking at here on this graph is increasing, decreasing, constant intervals. All right. Now, when we're talking about increasing, decreasing, or constant intervals, if it's increasing, it's going to be moving up. Okay? So when we read these graphs, you've got to be careful to think, okay, don't follow the arrows. Read it left to right like you would a book. Okay? So moving left to right, what's the blue line doing here? Is it moving up as you go to the right? On the left side of the graph? Yeah, it's increasing there. Increasing moves up and to the right. So that first little leg from way down here up to that point right there, it's increasing. So the interval for that is what we want to report. We want to tell the interval for that. The interval for that particular part of the graph is from negative infinity up to what x value? -2. Okay? So that's an increasing interval. This piece right here is an increasing interval. So that's that one. So I'm highlighting just to associate those two together. What's going on with this piece? Is that still increasing? No, it's flat, isn't it? It's constant. It's constantly the same level. So it's level and flat. So that would be a constant interval. What would the interval be for that? Up to 7. That's right. So that piece and that interval go together. They're the constant one. Now, what's this last part here doing? It's increasing as well. So it starts at what? And goes to infinity. Good job. We don't have any decreasing intervals here. What would a decreasing interval do? Yeah, it would be going down and to the right, actually. It'd be moving diagonally down to the right. Okay? We don't have one of those in this particular graph. And that's okay. You don't necessarily have to have one of each of them at all. Okay? So we don't have one there. We would write none there, probably, if they ask us to tell.
So on these problems, you just ignore like the y, you just look at the x-axis the entire time?
Absolutely. The x values are what you're going to put in your intervals. The y values don't matter. Only thing the y values are doing are setting where it's going up and down at. So the x values are the only things you worry about with those intervals of increase and decrease or constants. Okay. So really straightforward on the increase decrease, and they don't try to make it a very complicated graph when they do that. They're very straightforward and define points out of that, so it's not anything crazy. Okay. All right. That is section 2 something 2-3. That's all right. We got 2 sections left, and you know, a little bit of stuff about those. One section is really short, and the other section is taking it and doing some stuff with it. So I think we're out of here probably by 2 o'clock today. All right. So just hang with me just a little longer, and we'll get out of here. Okay. All right. Section 2.6 is where we're going to be, and it's the graphs of basic functions. All right. There's a thing we need to talk about. It's called continuity. Continuity. The first part of that word is the root of continuous. Continuity talks about continuous functions. So we'll define that: continuous functions over an interval Normally that interval is going to be the entire domain, but sometimes they'll say, is this continuous from 6 to negative, or from -6 to +4? Something like that. They might ask for a certain interval, but most of the time it's saying, big picture, is this continuous, discontinuous? The best way for me to describe this to you, a continuous function over an interval or the entire domain can be drawn without picking up the pencil or pen, whichever one you're using. Okay, so some sketches of a continuous. Here's a coordinate plane. A continuous graph. This would be, that one would be continuous because you can take your pen and trace that without picking up your pencil. You never have to pick up your pencil. Okay, so this would be continuous. Here's a coordinate plane. That one would be discontinuous because there's no way to trace that and get from here to here without picking up your pencil. Okay, so that's where the continuity breaks apart. So it would be called discontinuous. Okay, and then I'll draw another example of a discontinuous one that's a little more subtle discontinuity, and that might be one like this where you have that going on, where there's that empty circle that's right there. That empty circle there is a skipped point. That's like that x can't in the denominator kind of domain breaks apart. So that would be a discontinuous graph. Discontinuous means you got to pick up your pencil to skip a number, or you got to pick up your pencil to move to another section. Okay, so that's a fairly easy concept. Look at the graph. Is it continuous, discontinuous? That's what they're going to ask you to do. And if you have to pick up your pencil to draw it, to get from one piece to the next, it's discontinuous. Easy thing to do there. All right, so let's look at some basic functions. So you might hear this called the family of functions or the parent graphs. You may have heard that before, but it's the basic functions. And the first one that we're going to talk about is the identity function. F of x is equal to x. And I'm going to use my graphing calculator to kind of help me draw some of these because it does a much better job than my hands can do. So I'm going to use that. And it'll help you kind of get an idea with your graphing calculator how to graph things. So if you don't have your graphing calculator already, which is probably most of us, you can go back and watch this video and it'll show you how to graph an equation with the calculator. So here I am with my graphing calculator. I'm going to hit this y equals button. And I'm going to clear out all this junk that I have from somewhere else. And I'm going to type in just y equals x. So I just type the x. To get the x, right there beside the green alpha button, just hit it once. And that'll get you x. And I'm going to hit graph. And I'm going to, just to make sure my window is set up right, I'm going to hit zoom 6. Yeah, and it wasn't set exactly right. It was a little wider than it should have been. Okay, so that changed the graph just a little bit. It looks a lot the same, but the scale was a little different. That gets you to the default window, which is where we want to look at this stuff for today. Okay, so that's the graph of the identity function. Okay, notice that there's no breaks in it. There's no loops. There's no dips, humps, troughs, anything. Okay, it's just a straight line, goes through the origin and goes up and to the right. What would the domain of that be? Remember, we have an equation. It's f of x equals x. Is there any red flags? I don't think there are. So the domain, if there are no red flags, what's the domain? Yeah, in negative infinity to positive infinity. All real numbers. Another way to say that. The range on this would also be from negative infinity to positive infinity. Domains where we hang our hat most of the time, but we'll mention the range on some of these to get an idea. And so identity function looks like that. It normally has a domain of negative infinity to positive infinity and a range the same, negative infinity to positive infinity. And so identity function, being able to recognize that graph is what we're after here. The second one we're going to deal with is the squaring function. Squaring function. F of x equals x squared. Very, very simple equations in this thing. All right. Let's look at the graph of that. So I would go back to my y equals menu. I'm going to clear out the identity function that I had, and I'm going to hit x and then squared and get it to graph that. So I'm hitting the graph button after I type that. There's that loop shape. We drew one of these earlier in the before lunch when we were graphing. Maybe it was right after lunch when we started graphing some equations. Okay, so very, very simple picture. It has a domain. No square roots, no x in the denominator, so it's negative infinity to positive infinity. The range for this thing is from 0 to infinity. In its original state, it's from 0 to infinity. We did x to the first power, did x to the second power. Let's do the cubing function. Which would be f of x equals x to the third power. Okay. Graph that thing. Go to y equals. I'm going to clear this one out. X raised to the third. So basically, it takes one side of that squaring function and bends it down. This is kind of what it looks like it does. It's a little steeper, a little more straight up and down than the squaring function is, but that's what happens. And its domain stays the same. Negative infinity, positive infinity, because we don't have any square roots, we don't have any x's in the denominator. That's the reason it stays the same. The range changes on this one back to negative infinity to positive infinity. All right. Number 4. Now we're going to get into the square root function. F of x is equal to the square root of x. Now this one definitely has a problem in the domain. The domain for that would be from 0 to infinity, because we got an x in front in the inside of the square root. X is greater than or equal to 0. That's what that comes from. The range for that one follows suit. It goes from bracket 0 to to positive infinity. And let's look at the graph, and I'll kind of show you why the range stays the same as the that. So second x squared to get the square root function, and hit the x. And there's that graph. What it really does is takes one side of the squaring function and lays it on its side. Is absolutely what the square root function does. Is it reflects it across the y equals x line, but that's a whole thing we'll get into later. So picture that. Paste it through x. Why it stretched out like that at all? So there's that graph. Okay. So we can see the domain goes off toward positive infinity starting at 0, and the range does the same thing. Starts at 0 and it keeps going up as it moves out here toward the right. It keeps going up out of that. So, so the square root function. We did the squaring function and then the cubing function. So we're going to do the square root function, and then we're going to do the cube root function, which is the fifth one. And then I only have one more after that. And y equals the cube root of x. And it has a domain of negative infinity to positive infinity and a range that's the same. This one is a little more straightforward in that it takes the cubic function and really does just lay it on its side. Just like that. It looks, perfectly laid on its side. The cube root is the cubic function laid on its side. So being able to recognize these graphs based on their picture, and then just know the general information about their domain or range is going to be helpful as we move forward. So the last one, the sixth one, is the absolute value. I think it's the last one, yeah. Absolute value. The absolute value makes a V shape, and it's a function. And I guess technically I should have written this. I didn't write it as f of x. It should have been written as f of x. It's a function as well. The absolute value of x. So straight up and down bars, that's absolute value marks. The domain of the absolute value is all real numbers, negative infinity to positive infinity. The range is from 0 to positive infinity. Because remember, absolute value is a distance away from 0, so it's always positive. Distance is always positive. I've never seen a tape measure with negative numbers on it. They don't make them for measuring distance with the negative numbers there. So the graph of that, a little bit more difficult to get the absolute value, just like the cube root was. You're going to go to y equals, clear that out, hit math, and then press the right arrow key. And this ABS, that's absolute value and of x, and then hit graph. And there's that V shape that I'm talking about. It makes a V shape. Absolute value graphs will always make V shapes. They may be, scooted over, moved up or down, flipped over, upside down like a housetop looking, but they will always make a V shape. So keep that in mind as you're looking at things. V shape for the absolute value. Okay. So kind of try to visualize, though, if I say the identity function, you've got a picture in your head that you can recognize. If I say the absolute value graph, visualize in your head, it's the V shape. If I say the squaring function or y equals x squared, you got that U shape in your head, the parabola shape out of that. If you can get that, you're doing good. Okay. So what I want to do next, last section of the day, and the last section will be covered on your first exam, is section 2.7, and this is transformations. All right. Now, with transformations, there's a few different things that happen that we're going to talk about, and we're going to be able to describe them. They're not necessarily worried about us drawing the graphs as much as it is just transforming, being able to describe what's happened based on some information that we have. So there's stretching and shrinking that can happen. All right. Under stretching and shrinking, there's vertical stretch or vertical shrinking. Did anybody ever play with silly putty as a kid, or maybe you still do? But when I was a kid, we had silly putty, and every Sunday or every day there was a comic strip in the newspaper. Nobody takes newspapers anymore, hardly. So, but if you took that silly putty and you patted it out, and then you put it over the top of Garfield and pressed it down, and when you pulled it off, Garfield was on the silly putty. The ink transferred, and then you could take that silly putty and stretch him out. If you stretched him this way, it made him skinnier. And that would be what we're talking about, a vertical stretch. So a vertical stretch is going to take a graph like the original absolute value graph. It's like this. If we do a vertical stretch, it's going to make it look skinnier because it's going to pull it up. So that's a vertical stretch. A vertical shrink would be like taking that silly putty and Garfield's on there and you push it down. It makes him squat out a little bit, right? So it's going to widen it out. So the absolute value graph, if we do a vertical shrink, it's going to start here and it's going to widen out further and look squattier, I guess would be the right way to the way I would describe that. The way that happens is that you're going to multiply. It takes multiplication to do a shrink or a stretch. Tongue's getting tied. So it takes multiplication to do this. Shrinking or stretching is multiplication. Tie those together. Okay. It's taking a number times the original function. Whatever the original function is, this is the original function. So that's like one of the basic functions that we just talked about. And we're multiplying by something. If a is bigger than 1, that's a vertical stretch. If a is between 0 and 1, that's a vertical shrink. So if we're multiplying by a big number on the outside, stretching it. If we're multiplying by a small fraction on the outside, like 1/2, 2/3, anything less than 1 but bigger than 0, then we're going to shrink it. That's what we got to be able to recognize, okay? So examples of that would be, f of x is equal to 2 times the absolute value of x. That right there is a vertical stretch. Let's call that example A. Example B, f of x is equal to 1/3 x squared. X squared. That would be a vertical what? Shrink, because that's a small number, right? Doesn't necessarily matter what function that we've got here. It's going to be one of those original ones that we just went through, the basic graphs of those, But that number in front that's multiplied is going to tell us vertical stretch or shrink. It's on the outside. Anything that happens on the outside is going to be vertical. That's an important concept here. Anything that happens on the outside is going to be vertical. When you deal with the horizontal stretch and shrink, that happens on the inside. So you're taking the original function and something's happening to x, you're multiplying to x on the inside. And with that one, it's a brain bender here, guys. It's the opposite. If it's a big number, it's a horizontal shrink. If A is between 0 and 1, it's a horizontal stretch. The opposite happens on the inside. That's the way you got to think about it. Opposite things happen on the inside. So examples of that, f of x, if we put the 2 on the inside of the absolute value, looks a lot like example A, but the 2's not on the outside, it's on the inside. This is going to tell us it's a horizontal shrink. Or compression would be another way of thinking about compression, shrink, that thing. Example D, if we had, some function and the number, it's a, 7/8 x, and then that's to the third power. Because it's on the inside, that tells us that will be a horizontal stretch. Multiplying is stretching and shrinking. Outside, big number stretches, little number shrinks, just like it should. Inside, the opposite stuff happens. It's like turning a shirt inside out. It works backwards, right? So inside, small number stretches, big number shrinks for horizontal, okay? All right. What if that number that we multiply by is a negative? What happens then is called a reflection. Reflections across the x-axis happen on the outside. If something reflects across the x-axis, remember the x-axis is sideways. It's going to flip it up or down. It's going to be a change in vertical direction. Okay? So if something flips across the x-axis, it starts here and flips down here. So it changes things vertically. So that's why the x-axis across it is on the outside. Across the y-axis is on the inside. Because it's going to flip this way. So it'd be pointing that way, and then it points the other direction. Okay? So that moves it the opposite direction as you think it would. Okay? Now, last type of transformation is a translation. A translation is fancy words for moving left or right, up or down. That's a translation. Okay? Left, right, up, or down. Okay? If we take the original function and we add or subtract a number on the outside, let's call it the letter B, that moves the graph vertically B units. So f of x is equal to x squared plus 3. So plus 3 and rotate. What that does is it moves it up 3. If it says f of x absolute value of x minus 5. The minus, that's down 5. Outside is vertically. Okay. Inside's going to be horizontally. Okay. So y equals f of x plus b on the inside. So for example there, if we had f of x is equal to absolute value of x minus 3, you would think the minus would move it to the left, but it's the opposite because it's inside. Remember, the opposite happens on the inside. So your inside out shirt goes the backwards way. So it would be right 3. If you had f of x is equal to x plus 4 squared, that'd be left 4 units. Horizontally, going the opposite. Just like a horizontal stretch, a big number made it shrink on the horizontal compression. A small number made it stretch out horizontally. It's the opposite of what happens with it vertically. Okay. Now, let's look at a few problems and try to describe the transformation that happens. Okay. Just a few of these, and then one more thing, and we're pretty much almost done for the day. A little longer than I thought it was. All right. Describe the transformation. All right. F of x is equal to 3x squared minus 7. What did that do to the x squared graph? What transformations have happened here? And I don't know what letter this would be. I'm going to call it example A, just for this first time we've really done something completely. Okay, so what does the 3 in the front do? That would be a vertical stretch because it's multiplying times the x squared. Anytime we're multiplying to the x or to the function, it's going to be a stretch or a shrink. That's a big number. It's bigger than 1, so it's a stretch. It's on the outside. It's vertical stretch. Okay. The minus 7 is on the outside. It's not inside parentheses, so that would be down 7. The vertical stretch, and then move it down 7. Say we had this function, 1/2 x plus 4 cubed plus 13. What does the plus 13 do? It's a plus 13. It's on the outside, so that's going to move it up 13 units. The minus 4 on the inside, or the plus 4 on the inside, is a horizontal translation because it's adding or subtracting on the inside. It's horizontal. Plus 4 is going to mean move which direction 4 units? Not up because it's on the inside. Not down because it's on the inside. Inside's going to be horizontal movement, left or right. Okay. The 13 is on the outside, so that's the up and down movement. So it's opposite on the inside. Remember, inside out shirt. Opposite on the inside. So that would be left. 4. What does the 1/2 outside do? A small number on the outside. Since it's multiplying on the outside, it's vertical shrink. Vertical shrink because it's a small number on the outside. Let's try another one. Absolute value of 2/3 x minus 8. What does the minus 8 on the outside do? Moves it down 8. Two. Yes, sir.
So if you have a negative number on the outside, that automatically means, it might just, that automatically means it moves down, right?
Yes, if you're subtracting on the outside, it's always going to be down. If you're adding on the outside, that's going to go up.
Okay.
Plus a number on the outside's up, minus a number on the outside's down. That you've got the right idea.
Okay.
All right. Now the 2/3 on the inside. It's on the inside. So anything on the inside of the parentheses or grouping symbols is going to tell us it's horizontal. And it's multiplying, so we know it's a stretch or a shrink. So that number is a small one on the inside. So a small one on the inside means a horizontal what? Stretch. That's right. Remember, it's the opposite of the outside stuff. If it's happening on the outside, it's vertical. If it's happening on the inside, it's horizontal. That'll help get you, if you can keep that in mind, that'll help get you going on that stuff. Okay. All right, let's look at a couple of tests here before we get out of here on symmetry. What's it mean to be symmetric? Do y'all know what that means? It's kind of a geometry term, so it's one of those things that not everybody remembers because you only take one geometry class in high school. Yeah, if something is symmetric, that means that it folds perfectly in half, and would match up. That's what symmetric means. So that's great if you've got a piece of paper that's got every graph on it and you can fold it and see if it matches up. But that doesn't ever happen. You don't have every graph in the world of every equation, and you can't wouldn't expect you to graph every one of them on a piece of paper and then check it. Because some graphs are really, really large, and some are so small that you can't do that in a timely fashion either. So tests for symmetry are fairly simple. Okay, so if we want to test for y-axis symmetry, so that means you could fold it at the y-axis and it would match up. You want to plug in negative x. Okay, if everything stays the same, it's symmetric about the y-axis. Okay, if everything stays the same. If anything is different, once you simplify it, then it's not symmetric about the y-axis. Okay, so for example, we have this function f of x is equal to x squared plus 4. Okay, and I plug in a negative x. Negative x squared plus 4. So I'm simplifying this. Negative x times negative x would be positive x squared plus 4. Is that the exact same thing as I started with? Is this the same as that? Yeah, it is. So that would mean that this one is symmetric about the y-axis. So okay, so that's the test for y-axis symmetry. All right. Let's look at x-axis symmetry. X-axis symmetry set equal to negative y and solve for y. Same rule. If everything stays the same, then it's symmetric to the about the x-axis. If anything changes, it's not. Okay, so if we took that same function, f of x, we call this example e, equals x squared plus 4, and I plugged in negative y equal to that, and then I get y by itself. The only thing to do to get y by itself is to divide everybody by negative 1. Negative x squared minus 4. Did everything stay the same? No. They're both the opposite sign that they were. Not likely that everything stays the same for checking this. So that's not symmetric. About x-axis. Okay. There is one more type of symmetry. And that is of the origin. It's both x and y axis symmetry. If it is both x and y axis symmetric, then it has to be origin symmetric. If it is only one of them, then it's not origin symmetric. Okay, so we're going to look at an example that does both of those. So our look at an example. Example F. Let's say we had x squared plus y squared is equal to 16. So if we're checking for y-axis symmetry, we're going to plug in a negative x and see if it turns out to be the same. Well, that right there turns back into x squared. And what do you know? That turns exactly the original. So it is y-axis symmetric. Let's check x-axis symmetry. And with x-axis symmetry, this one wasn't a regular function. So, instead of setting it equal to negative y, I'm just going to replace y with negative y because that's what we really are doing anyway. Okay. And then, what do you know? The same thing happens. It turns back to positive y squared. So it is x-axis and y-axis symmetric. So that means it has to be origin symmetric. It's symmetric to all three. That particular equation is. Okay? So for y-axis symmetry, plug in a negative x, work it out. If it's the same, it's y-axis symmetric. If it were x-axis symmetry, plug in a negative y in the place of y, work it out simplify. If it stays the same, then it's x-axis symmetric. If it is both x and y axis symmetric, then it has to be origin symmetric. Okay, that's how you're going to test for origin symmetry, is test for the other two. Okay, now since we did the negative x thing, then that opens up this thing with the odd and even functions, and this is last thing, odd and even function. Okay, odd and even function test. It's the same as y-axis symmetry. Plug in negative x. If everything is the same, it's even. If everything is opposite, it's odd. Anything else? Neither. Okay. So we're going to plug in negative x into the problem. If everything turns out the same, it's going to be even. If everything turns out the opposite of what it originally was, then it's odd. If any mixture of that happens, then it's neither. Okay. Most functions are neither. Most regular ones that you're going to encounter, but they're going to throw in the ones that they're special in this section because that's what they're talking about. So odd, even, or neither. That's the question we're answering for this example. Example G. Here's our function. F of x is equal to 8x to the fourth minus 3x squared. If I plug in negative x, any negative number to an even power turns back positive. So both of these end up being exactly the same as they originally were. That and that are the same, so this is even. A shortcut to knowing if something is even is looking at the exponents on the variables. What do we know about on the original problem? What do we know about both these exponents on the variables? They're both even, right? So that means that the function has to be even. Okay. If there were another piece, for example, if you had f of x is equal to, maybe 6x to the fourth plus 5x squared plus 7. Those first two have even exponents. But what's the degree on the third term? 0. That's not an even number, right? So this one could not be even. Okay? It would be neither. Okay? For that one. Even for the first example, neither for that one using the shortcut method, which is going to work every time if you do it correctly. Let's say we had this function, 6x to the third minus 9x. What's the exponent or the degree of each term? What's the degree of this first term? 3. The degree of the second term is 1. Both of those are degree that are odd, so that means it's an odd function. If you did the actual math that's involved, it does work so that it's negative 6x to the third, positive 9x. It changes it to the opposite. But you can use that shortcut. If it's got all even degrees on each term, then it's an even function. If it's got all odd degrees on a term, it's an odd function. If it has a mixture of the two, then it's neither. That's the really the shortcut way, and the way that I do it anytime I need to know that if a function is odd or even, I don't really do the negative x plugged in. That's the true test, but that's not how, it's kind of like, how you're supposed to do something, but there's a quicker way. Okay. So that's a helpful thing there, as far as that goes. All right. I'm going to write some suggested practice problems that you can look at in your textbook to help you prep for the exam, give you an idea. It's gonna have far more than you'll ever need to do on it, but just pick some. My suggestion is you pick a few from the front of each section, a few from the middle, and a few from the end. Maybe 10 problems in each section, that just to practice them, make sure you're doing them right. And then the labs are also going to help you get prepped for the test as well. And then feel free to email me questions that you would have about problems in particular. Pictures are always helpful of the problem. That way I know I'm looking at the same one you're looking at, and that sort of thing. And especially, it being summertime, I'm not always at home and I'm not always near my textbook. So if you email me and say, hey, I need help with page 206, number 17, I may not be near my stuff, but if you take a picture of it and send it to me, I've got it and I can help you straight from my phone wherever I'm at. So, and I don't mind doing that at all. So don't hesitate to that. So R1 on page 6, the problems that we covered were from 1 through 93. Pick some. Look at the ones. There's going to be ones you don't need to even look at because you know how to do. So don't think you've got to do any particular portion of these. This is all just to get you ready for the test. R2, page 17, 1 through 47. R3, that was the really long section, but it only covered 43 problems. Then 2.1, that was the rectangular coordinates that we talked about and graphing lines. 1 through 59, a lot of different stuff in that one. And then, page go there. 2.3 is the next section we covered. Page 199, 1 through 85. I would suggest you only work on the odd ones because in your textbook you'll have the answers to the odd ones that you can check yourself with. So odds obviously on that because it's just makes better sense to, if you know what you're trying to get as an answer, you got a better shot at it. And then on section 2.6, which was the basic functions, there was only a very small number of problems that we looked at from there. Let's just do 1 through 16. That gets all of those. And then, or 1 through 15, excuse me. And then 2.7, which is the transformations and the odd and even stuff that we just looked at. 1 through 93. That was that whole section that we did there. So you can see the ones that have more problems, we did the entire section of. The others, we didn't do as much of that. And that gets us everything for today.